Okay, so we're going to start chapter 6. We'll get just started on 6.1. So 6 is about matrices. So matrices will be what we're going to use to help us solve systems. So we're still going to be doing systems, but this time we're going to be using matrices for that.
So, like, how many more units do we have?
So you'll have through chapter 7 will be on your final. So chapter 6 and then we have 7. So and we'll finish 6 before spring break. So not too much to do after that. And then you'll have your final, which will be chapters 1 through 7. It'll be over everything. Yeah, because it's the UMKC final. And, you know, this class is typically just a semester class, so we have to have the final over everything. But we'll have about 2 weeks to study for that. So plenty of time to study for that, prepare for that. And then after that, no, none of it. No,
Not at all. Oh my god.
No.
Oh my god.
It'll either be depending on what our schedule is, because that is, we'll be taking it at the very end of April, which is during usually the block scheduling because of EOC. So it'll either be a 90-minute block final, or if we have normal periods, it'll be a 2-day. So
What do we do after that?
we are going to do a project after that. Nothing too hard, nothing too much. But that what we do after that will go into your high school grade, but not your UMKC grade. Your UMKC grade will stop after the final. Okay? Alright, so we're almost there. We're almost there. Alright. So we'll get through, we'll talk about A and B, and we'll start discussing C today. But objective C is pretty long. So we'll kind of just start talking about it today. The first thing that we'll do is just talk about what a matrix is. And then we will go from there. So we're going to learn how to solve systems using matrices, but different ways. So this first section, we're going to learn one way to do it, and then we'll learn a couple other ways throughout the chapter as well. Okay, so first of all, a matrix is a rectangular arrangement of numbers called entries. So each number in the matrix is an entry. So matrices will be enclosed by brackets, and they're named using a capital letter. So when we talk about matrices, like we'll describe them like this is matrix M or matrix A, matrix B. When we write it down, we'll use capital letters. So the horizontal entries are your rows. So this is row 1, this is row 2. Okay, and then your vertical entries are your columns. Okay, so you want to know which ones are rows, which ones are columns. I think about, columns are vertical because I think about like the columns on a house. or quad at Mizzou, those columns, they are vertical pillars, so vertical entries are your columns. And when we talk about the size of the matrix, the size will be the number of rows by the number of columns. We use that little multiplication symbol, but when we read it, you read it as rows by columns. Like if you're talking about the dimensions of a room. Okay, so matrix M has how many rows? 2. And it has how many columns? 3. So the size of matrix M is a 2 by 3. It is a 2 by 3 matrix. We also can, if we need a specific entry in the matrix, then we can name that. So let's identify the row 2, column 3 entry. Okay, so I'm looking at matrix M, and if I want a specific entry, then I'm going to use lowercase m because I'm going to take out just one entry out of that matrix. So the whole matrix is capital M, lowercase for a specific entry. And I want the row 2, so as a subscript, 2, and then column 3, so comma 3. So those are subscripts. The 2, comma 3 are subscripts. So if I want the row 2, column 3 entry, then I go to the matrix. So row 2, column 3, that would be -5. So M 2, comma 3 is -5. No, there's not a, you can have a matrix of any size, but the size does matter because certain operations can only be performed if some sizes match up. And so that's why we have to know how to write out the size of the matrix. So there's not a limit, but the size will matter when we go to do operations with the matrices. Okay. So that's kind of just the description on what a matrix is, the parts of it. But we're going to talk now about an augmented matrix. So using an augmented matrix is one way we are going to solve systems. So I'm going to be given this system, and then I want to write the augmented matrix from this system. All right, so what the augmented matrix is, it's just basically writing that system without the variables or the operation sign. So you're not going to do the addition or subtraction. So my first equation, 2x minus 3y plus z, I'm going to write 2, negative 3, and 1 for 2x, negative 3y, 1z. And then I do need to separate what it's equal to, so I do that with a vertical line. And then I'll put the negative 1 over here. And then that will close your matrix there. Okay, so then if you look at your second equation, you don't have an x. So the coefficient there is 0. Okay, so 0, positive 5, negative 2, and 7. And then go ahead and write out the third row there. So that will be 4, 1, negative 1, and 10. So that's what an augmented matrix is. Okay, then we can separate the parts of this augmented matrix into our constant matrix, which is the numbers without variables in our original system. So these numbers don't have variables. So that's negative 1, 7, and 10. So what would the size of this matrix be? How many rows are there? So rows, remember, are horizontal. Okay, so 1, 2, 3 rows. And then how many columns? Just 1. That's a 3 by 1 matrix. Okay, the coefficient matrix then is the other part. It's the numbers with the variables. So back in your system, it's right here. Okay, so this part of the augmented matrix. So I'm just copying that part down. How many rows does this matrix have? 3 rows, and how many columns? 3. So that matrix is 3 by 3. If the rows and columns are the same number, then it's called a square matrix. Think about a square. Squares have all the sides are the same. Okay. Questions about that? Okay. So we take an augmented matrix, and we are going to want to do some row operations to it. And get it to look a certain way so I can identify what my variables are. So I have these 3 elementary row operations that I can use. So basically what that is elimination, the elimination method, just without the variables. You don't need to write this matrix down yet. So if you have a matrix, you can swap any two rows. You can change, just put the middle one on top or the middle one on bottom, top one on bottom, whatever. You can swap any two rows. You can multiply any row by a non-zero constant. So you can multiply any row by any number. And then you can add any two rows and replace one of them with that sum. So that's the elimination part. So we do all of that. That method, that main method, is, this is just the name of it. So we get our matrix to look like this. So it's called reduced row echelon form, Gauss-Jordan, if you see that name. And you get your augmented matrix to look like this. So I am going to use just the number sign, like the pound sign, meaning this could be any number. But that's what you get your matrix to look like. So you do those row operations until you get 1, 0, 0, 0, 1, 0, 0, 0, 1. And these could be any number. So for example, so this gives me the solution to the system. This tells me my solutions are 3, -2, and 7. So my answers are 3, -2, 7. And here's why. So look at this as a system. So remember, over here, the left side is your coefficient matrix. So that's 1x plus 0y plus 0z equals 3. So that's x equals 3. Here is 0x plus 1y plus 0z equals -2. So that tells you y is -2. -2. Okay. And then this one is 0x plus 0y plus 1z equals 7. And so that's z equals 7, which gives you that solution. Okay, so that is reducing the matrix as far as you can go. We don't have to get all the way there to find our solution. What we want to do, so what we're going to do is this method here, we're going to triangularize. Okay, so triangularizing is part of this reduced row echelon form, but we can stop after we triangularize because we can find our solutions. We don't have to have it look like this. So what we want to look at our goal is going to be to triangularize. So we want it to look like this. And again, I'm going to use the number sign, the pound sign to represent it could be any number. Okay. We say triangularize because we get this triangle of zeros. once we get there, we can find the solutions of our system. So for example, we'll be given a system. You write it as an augmented matrix, and then you triangularize, you get these triangles of zeros. So that's after we've done a little bit of work. And let's say this is what we get. So after we've done those row operations, which we'll practice next time, but we get our triangle. So this is after we've done the triangularizing part. So I have my triangle. Then I can find x, y, and z by back substitution. So by back substituting. Okay, because what that says, we can start with this. That's 0x, 0y, so 3z equals 9. That tells me z equals 3. So when you back substitute, you have to include the variables. Okay? Now, go to the middle row and plug 3 in for z. So that's 0x plus 6y plus 2 times z, which is 3, equals 24. So y is 3. And now take both of those so plug this in for z and this in for y and find x. So that's 2x minus 1 times 3 plus 4 times 3 equals 17. This is 9, and you get x equals 4. So your solution is 4, 3, 3. So what we will do on Tuesday is figure out how to get our matrix with our triangle of zeros. And once we get there, we back substitute to find x, y, and z.